A warm good afternoon to all the delegates who have joined us from India. A good morning to our delegates from people from Europe and from the US. And an evening to all our delegates from Asia Pacific. My name is Kailash Shirodkar and I welcome you all to day 4 of India Water Innovation Week. Our topic today is something that is critical across the globe. It's recycle and reuse of wastewater. And without taking too much of time, I would now hand over the session to our moderator, Mark Barker. Mark is the CEO of Vex Global based out of London. And I'm now handing it over to you, Mark.
Thank you, Kailash. And welcome to everybody for this afternoon of discussions about water reuse and recycling. Thank you, Kailash, for inviting Vex Global to participate in the Indian Water Innovation Week, and in particular for giving us the chance to cooperate in putting together these sessions today. For those of you that are not familiar with Vex Global, I'm the CEO. It's an international summit which every year brings together some of the world's leading experts, some of you whom you're going to be hearing from this afternoon, to discuss critical issues relating to the world of water, and in particular, the leading role of the sector in facilitating the transition to a global circular economy, which has been a recurrent theme of many of the sessions this week. The transition to a circular economy, of course, creates significant synergies for the wide adoption of water reuse as an alternate water supply. It offers environmentally sound solutions to the problems of water scarcity in a manner which is compatible with the principles of the circular economy. It's a huge subject for us to cover in the time that we have available today, but in order to give us a global view of this highly important issue, I'm delighted to be able to welcome Professor Dragan Savic, who is the head of the KWR Research Institute in the Netherlands, which was, I think, the first institution to detect the presence of the coronavirus in wastewater as a means of predicting future outbreaks. He's also a co-founder and director of the Centre for Water Systems in Exeter University, an internationally recognized group for excellence in water and environmental science research. So here to give us the benefits of his insights into the future of water reuse and recycling, I'd like to welcome Professor Dragan Savic. So it's over to you, Dragan.
Thank you very much, Mark, and thanks to the organizers for giving me the opportunity to speak to you today. I'm very, very excited about that. And you know, because water reuse, recycling, and the reduction of water use is one of the key topics for the future, not just of one institution of the country, but of the world. With that, I'd like to start just a brief background of the KWR Water Research Institute. Our main motto is bridging science to practice. You can see that we have a long history of working in the field. We are independent and not-for-profit entity since 2006 with over 180 scientists working in this area. And our main goal is sustainable water provision in the entire water cycle. But we also kind of focus in this case, more on the urban water cycle. So you can see here from tap to wastewater. And then what do we do with the wastewater, whether, you know, reuse ends up in agriculture or industry and so on, and whether it goes back into drinking water. So let me just remind everybody, this is the view from the space of our beautiful blue planet. And my question is, to all of you, do we know that we have finite supply of water on the planet? This is when if you scrape all the water from our beautiful blue planet, this is how much we have it. And this has been from ages, no more, no less. And then the smaller there, you can see that we have fresh water much less. And then if you blinked, you must have missed it. This little blip here, it's the water in the lakes and rivers. So we have to have a really good or take a good care of it. The other thing is that the distribution of this pressure resource and distribution of people in the world is different. So in each of these, you can see, say, for example, for Asia, that percentage of globally available resources. So 30% of the globally available resources are in Asia, but 60% of the population. You obviously see that the geographical spatial mismatch. And then when you think about temporal mismatch, you know, monsoon season versus dry, summer versus winter, and so on. And then if you look at 70% of the water is being used in agriculture, and then there is movement for people going into cities. Over half of the world population is now in the cities, and then 40% increases in population over the next 30 years. So we are facing big challenges. So why wastewater? What is so special about wastewater? Well, over 80% of our wastewater flows goes into the nature untreated. And that's a sad fact and reality. So we want to reduce that amount of water that is going into the environment untreated, so reducing pollution of the ecosystems, and reuse, so treat and use it for various usages. And this is just to give us a better idea of the amounts produced. So you can see this is wastewater produced per capita per year. So this is how kind of each and every one of us uses in a year if we live in sub-Saharan Africa or in North America or any other part of the world. So you can see huge differences in the wastewater production. And in the world, we're talking about 95 meter cube per capita per year on average. I can tell you total is 380 billion meter cube. But what does it mean really? That if anyone has visited Niagara Falls, huge, beautiful falls in North America, well, that's 5 times what flows through Niagara Falls on a yearly basis. So think about that. That's the amount of wastewater generated in the world. And that's why circular systems, looking into water in the circular economy, what we call WISE here, is very important. And then if you look into, but it's not just water. It's not just water. Wastewater is not just water. We're looking into valuable nutrients in them. So you can see how much, what is the worth, revenue generation, if we used all the nutrients, potassium, phosphorus, nitrogen, recovered from it, how much of the fertilizers that we produce every year we can replace by those nutrients, and how much are they in the wastewater. So again, think about WISE, water in the circular economy. This is our contribution from water professionals and users to the world. And then the energy. You know, wastewater has 5 times more energy embedded in it than it's needed for treating that wastewater. So if we are able to take the wastewater out of it, you could see here in the graph how much we can actually gain out of it, how many households we can feed with electricity if we needed it. So remember the keywords: WISE, water in the circular economy. And if we move on, I'm having technical difficulties. Yes. Wastewater treatment and reuse is not new. It's been, as the world has been around, or humans, we've been reusing wastewater. So these are the example from the Greek island of Crete. prehistoric times, 3,200 to 1,000 BC, wastewater has been used for irrigation and agriculture. So what are the different applications? Agriculture, obviously, irrigation, landscape irrigation in our cities, and then industrial recycling and reuse. Industrial usage normally, or in many cases, don't require drinking water quality, recreation and environmental use. All of those non-potable urban uses, not for drinking, but for urban areas, groundwater recharge, unplanned potable reuse. I can tell you that many rivers in Europe, on other continents, what one city releases in terms of treated or untreated wastewater, the other city is using, downstream is using for water supply. And planned reuse. Recently, I think 2 years ago, the city in Namibia has been celebrating 50 years of using some of the highly treated wastewater. City of Windhoek was using that for augmenting their water supplies. This is an example that I'm showing you from the Netherlands. This is an example what KWR colleagues have been working with. This is the map of the Netherlands on the left, and different types of water sources. We have groundwater sources in the west, in the dune area. So you have large dune areas, so sandy areas, which are depicted here on the right top. Then you have on the top, you have fresh water. Then you have in the pink, you have brackish water, so mix of fresh and salty water. And then the seawater is at the bottom. So there is interaction there. And it's very important how much of this fresh water we have here to protect it from becoming brackish and saline. And then you know that the Netherlands is one of the biggest exporter of agricultural products in the world, I believe second in the world. And what you see here is the greenhouses in that area along the dunes, where they are producing quite a lot of those produce for selling in the Netherlands and abroad. So they have, or they need, constant and continuous irrigation. And this is an example where we have, in blue, you have those greenhouses in New Prinsenland, 260 hectares of modern greenhouse areas. And then on this area, you have production of sugar factories, and they use sugar beet. And those of you who understand the situation, sugar beet is done in a campaign, 3 months in a year, and they require lots of water. They produce lots of wastewater, but only 3 months per year, whereas these greenhouses require them continuously throughout the year. So what is the solution? We have the brackish environment there as well, and demand for irrigation, continuous irrigation, is greater than supply of rainwater. So what do we do? So this is the situation, September to January. That's the campaign when the sugar factory here is getting all that water produced. And then we have greenhouses here that need it spring and in the summer. So we have a solution where all that wastewater is treated to the level required for agricultural irrigation. Then we are putting them into groundwater to be stored, because you have that density difference between brackish salty water and the fresh water. We can keep it there. It's not easy, but we can do that, and then use it to bridge that time between supply and demand. Another application where we have underground drainage systems, so pipes, perforated pipes that collect water and drain it away, but then we use that system in reverse. to do sub-irrigation when it's needed for the plants that are being grown. So you can see Bavaria Brewery, that is food industry, but we are linking it to agriculture. The same thing we have it in Haaksbergen, domestic wastewater to agricultural application. All of it with this existing drainage system, but using it in reverse when we need to irrigate the system. So you have here on the left, you have two areas, area that was sub-irrigated and that wasn't sub-irrigated. So you can see the difference in maize here. When it was sub-irrigated, it was really nice. When it wasn't, I'm just going once again. When it wasn't, it's really yellowish and brown. That slide didn't work well. It was showing something else later on, but let me move on. We also at KWR look into quantitative microbial risk analysis. So we've developed the tools to see what are the risks of using wastewater in various applications. So we created this transparent, science-based online tool, which is also user-friendly. And this gives an example of how that tool, Aquaness, is used for water reuse applications. So we see here what is the quantity of microbial pollutants and then how they are reduced. So 1 log means 10 times less in the first treatment, then 2 logs 100 times less in the ozone treatment, then you have 3 logs when it gets to slow sand filtration. Then we use Monte Carlo simulation to look into uncertainties at each time step so that you can test different scenarios with these. So I'm just giving you an overview of some of the applications where KWR has been involved with reuse or wastewater reuse in various cases. So as a conclusion, I would say we need to move to responsible water reuse, where it's safe to use wastewater, treated wastewater. Requires incredibly interdisciplinary approach. You have to have health specialists, you have to have microbiological specialists, you have to be chemical quality specialists, you have to have treatment technicians. So we're talking about sustainable use of water. We need legislation and regulation, and sometimes regulation is much more stringent for wastewater that is being treated and reused than it is for drinking water. Then we have various treatment technologies that we need to understand. As I mentioned, health and safety, quantitative microbial risk analysis. Then we use, when we look into reuse, agriculture or industry, and also subsurface water storage. Quite a lot can be done through water storage in the groundwater, both temporally and spatially. So again, I will finish by reminding you of this integrated urban and natural water system. When we go from tap to wastewater, from wastewater, instead of having this effluent, we can actually use the water in agriculture, in industry, and some of it in the nature for evaporation. And then we go as a source for drinking water in the next step. With all of that, I thank you for your attention, and I wish you a very enjoyable session today.
Thank you, Dragan, for that excellent oversight of the technologies which will be driving the future of water reuse across the globe. We've just got a couple of minutes. I wanted to just ask you a question on a subject we were discussing a little earlier before the session, and that is, when looking at implementing new water reuse projects, how important is it to take into account sort of local, cultural and historical traditions of the region before deciding on to progress?
Yes, that's extremely important because I firmly believe that technology on its own cannot solve all our problems. It is a necessary kind of requirement, but we need to look into the human dimension of water reuse and recycling. We know there is quite a lot of misunderstanding about wastewater reuse among the public in general. And then locally, we have to see what are the current conditions and socioeconomic, but also religious reasoning about wastewater reuse. So all of those have to be taken into account and combined with the technology. So when I said we really need interdisciplinary approach, I have to give credit to all my colleagues who do this work, because they fully understand that, and we have a social kind of researchers, social science researchers, who are helping us inform the public and all the stakeholders what water reuse, recycling, and reduction of water use means to them, to the environment, and to the future of humanity.
Okay, fantastic. And just a couple of, we've actually had a large number of questions come in for you from the audience, and we'll by no means have time to answer them all today, but I'll just pull one or two out at random for you. One of which is out of overall energy available in wastewater, how much is it feasible to extract and is actually usable?
Yes, that's an excellent question. Can I just say, I'd like the organizers, if it's technically possible, to collect these questions and email it to me, and then I'll answer each and every one much later, obviously not today. But let me answer the question directly. It's very difficult to say that, because our technology is improving day by day, how we can recover nutrients and the energy from the wastewater. So I would say personally that we are down maybe between 10 and 30% right now, but we can quickly look into co-digestion and other ways of getting the energy out of wastewater and of the solid waste after wastewater is treated, so that the energy can be released through methane, through various other possible options. So I'm very optimistic, and I'm, in a short while, I would expect that we will get to the point of 60-70% efficiency.
Okay, it's quite remarkable. Just one, I think we've got time for one more question. Which tools is the Institute using for quantitative microbial risk analysis, Dragan?
Well, through various externally funded projects, we've developed this Aquaness suite, which looks into it. And that's for preliminary optioneering analysis to see what different ways of treating different treatment trains do to the risk reduction in terms of microbiological risk. So Aquaness is our main tool. It's an online tool, and as I said, it's funded from public and outside sources, so European projects. That's how it first started. So we're working with various stakeholders to improve the tool, but it's currently available, and people are, we're happy to share them. We have a networking organization called WaterShare, through which quite a lot of these tools are made available.
Hey, Dragan, thank you very much for the presentation and for the detailed answers to the questions. There are quite a number which have come in for you, and I'm told the organisers will be able to forward them on to you so that they can all be answered. I think you're going to be a busy man. But thank you very much for joining us and for that great presentation.
Thanks,
Dragan.
Thank you.
We now have 5 case studies covering a wide variety of water reuse projects across the globe. We're going to begin with a look at the wastewater strategies of the Municipal Corporation of Greater Mumbai in a presentation given by Mr. Atul Rao, who in his role as the chief engineer on the Mumbai sewage disposal project is leading a number of really innovative initiatives to promote the use of recycled water by targeting bulk users. So to learn a little more about Atul's work, I'd like to hand over to you right now.
Mark, the presenter is Dr. Ajit Salvi from, the Municipal Corporation of Greater Mumbai.
Okay, my apologies. Ajit, I'd like to hand over to you now.
Okay. A nice keynote address by Dragon Savvy. So I think with that, it will be easier for us to represent our case studies or presentation. So thanks to Dragon Savvy. So far I am concerned, I am from Municipal Corporation of Greater Mumbai, and this will be the small agenda for today's presentation. I will talk in a small detail about the existing sewage system, that is the current scenario, then present sewage disposal system, and mainly I will be focusing about the future plans, that is the treatment with recycle and reuse planning. That is the today's subject as such. And then what are the challenges? Already Dragon Savik has already discussed some challenges and some difficulties. I will also talk about these aspects, and then we'll conclude it. Presentation is not moving. Please. Next slide. See, this is the area for entire Mumbai, and basically this Mumbai is divided into 7 sewerage zones. So this is the topography of the Mumbai, and accordingly, let us say whatever that zones are there, Kulaba, Vardi, Bandra, Versova, Malad, Ghatkopar and Bandu. So that zones, it is visible on the map. So whatever sewage is collected, let us say a small example of Vardi, you can see on the map. So whatever sewage collected in that particular zone, it is collected at one particular terminal point, and then there is a treatment, and then it is discharged into the sea or creek, whatever possible. Okay. So this is in general, the sewerage system of Mumbai. It is divided into 7 zones. Now, Kailash, just see, because it is not moving. Okay.
There will always slight lag when you press click at your end. It will be a slight lag.
Okay. So this is the sewerage system of Mumbai. I am not going into all detail, but you can see that basically 3,850 MLD of the water supply is there, and whatever water supply that is converted into sewage as a thumb rule. Our sewerage system is almost 130 years old sewerage system, and at present there is a coverage of 68%. Number of manholes, sewerage system network is around 2,000 kilometers of the sewerage networks, and manhole covered is 73,213. Idea of this slide is what existing sewerage system is very vast and fully covered, though it is not 100% covering the city, but it is still almost it is covered. Now, if you see existing facilities, as I said in my agenda, I am going to talk about the existing facilities. So these are the 7 sewerage zones, and these 7 sewage treatment facilities are there. So out of that, only one, that is what first Kulaba, whatever I have marked in a red color, it is now newly commissioned with the tertiary treatment facilities. When I say tertiary treatment facilities, that means what there is a recycle and reuse facilities is there, and capacities are 37 MLD. This is just commissioned in April 2020. So this particular plant is newly commissioned, full tertiary treatment facility, and we are planning this particular recycled treated water that will be used for the reuse purposes. The remaining all other our facilities at Vardi, Bandra, Versova, Malad, Bandup and Ghatkopar, one can see that basically all these are the old facilities, and there is treatment level is almost at the level of preliminary treatment. In Vardi and Bandra, the disposal is through marine outfall. In Warsaw, Bhandub and Ghatkopar, the disposal is through lagoons. But we are not doing as such a big secondary or tertiary treatment is not done. So this is what our old system or existing facility. Now we are going with the new plans. So now for the future plans, as per the planning authorities and controlling authorities, there are new discharge standards set in India, and that is applicable to our municipal corporation also. The main aspect is what, say, so BOD 10, COD 50 and TSS 20. So these are the main aspects, and other things are also there. There is a total nitrogen control, phosphorus is also that limits are provided. The point is what, the new discharge standards are comparatively strict, and we have to treat up to the 10-20 standard, that is BOD 10 and TSS 20. Up to this standard, the treatment is required, and accordingly our planning has been, we are doing the planning, or planning is already done and it is to be implemented. Now these new projects, the best is on open technology. DBO contracts are there with the operation maintenance of 15 years as per the FIDIC condition. And there is a main aspect is what, there is a 50% capacity for recycle and reuse. That is what the main aspect of our future plan. Now, with this, so far the tertiary standards are concerned, which we are going to use for the reuse purpose. So still it is a stringent standard, BOD as it is 10, but TSS we have to go up to 5, and fecal colipump it should be below detectable limit. All other standards are, you can see on the the display. My idea is what, with all these stringent standards, we are doing the planning for the future, or we have to implement our planning based on these particular standards. Now, these are our proposed WWTF with the MLD capacities. So these are the future plan. So you can see that if as I said, Kulaba is already commissioned. It is having 37 MLD capacity, having full tertiary treatment facilities. That is what entire 37 MLD we have a capacity to convert into a tertiary treat, and it can be reused. Remaining all other plant, Varli, Bandra, Dharavi, you can see there is a maximum capacity at Varli, that is what 500 MLD, and minimum at Warsaw, that is what 180 MLD. But all plants, we are converting, there is a planning of 50% of the capacity to be tertiary treated, and it is to be reused as a recycle and reuse. No doubt, after that, there is a provision of the remaining 50% of the plant capacity to be reused in future based on the demand available for the tertiary treated water or treated wastewater. So based on that, the remaining 50% will also be, we will be going for the tertiary treatment. The idea is what, with this, this is the photograph of showing our commissioned Kulaba WWTF with a 37 MLD. My point is what, it is not only planning, there is already executed, and it is on the, we can see on the, diagram, on the presentation, the Kulaba treatment of WWTF with the 37 MLD already commissioned, and the tertiary treatment with the recycle reuse capacity, we are using that. We are planning to supply all this treated water, treated wastewater to the consumer for non-potable purposes. Now, for new projects, particularly Mumbai, there are some challenges in the implementation. Let us say we will talk separately about the recycle and reuse, but as such, with the secondary treatment and BOD 20 and BOD 10 and TSS 20, with this standard also, there are some problems. The main problem for us is what, there is an inadequate land. As you must be aware that Mumbai, everything is available except land. So that is a problem. There are some, this city is located on a coastal line. So there are some mangroves, and there are some problems for removal of the mangroves, and definitely we have to obtain the proper approval for that. Then clearances from the environmental ministries and coastal regulator authorities. At some of the places there is encroachments are also there. So before we go for the execution, we need to remove this encroachment also. Population growth, particularly the zone like Malad and all, there is a large change in the population, growth in the population. And as such, Mumbai is surrounded by all big municipal council. There is a large floating population is also there. And very important aspect is what? Basically what our new plants are there, plants, we have whatever plant. That is, some of the plants are located in the heart of the city, and at the same position, at the same place, we have to construct the new plant by keeping in operation old plant. So there is no separate land available. We have to keep in operation old plant also, and at the same place we have to construct, we have to go for the new plant with the stringent discharge standard. So that is the main aspect. My first point, I am already talking about the inadequate land, and this is adding another complication. Now, apart from that, then we are talking about the selection of the technology, low capex and all feasible. Then we are talking about the sludge disposal with the class A arrangement, so that it can be disposed of. Further, it can be further we can do the treatment for the further level, and as a part of a recycle and reuse, this sludge also can be recycled by removing the biogas, and then we can use it as a manure, and all these plans are also there. There is a planning for energy generation also. See, my idea is what recycle reuse is not only wastewater, as Dragon Savik already talked about that. Lots of other aspects are also there, and rather than only wastewater, we can consider it is as a factory itself, and we can recover so many things out of that. Now, recycle reuse, that is what today's discussion. The main problem, particularly in implementation, is concerned, as some of the points Savik has already discussed, but I want to make it in a specific way, particularly for our Mumbai. First of all, maintenance of the tertiary treatment facilities. So as such, as I shown, as such, at present, the tertiary treatment facilities are not available. And when we are going with such huge capacity plant, so that maintenance of that tertiary treatment facility is not an easy task. We have to go with that. Then provision of the distribution network. Such almost 1,250 MLD plus treated wastewater is available. So we have to make some arrangement for the distribution network, and that is also there. So this, after providing this distribution network, automatically maintenance of that distribution network is also a big challenge, because underground water network is there, there is an electricity network, cable network is there, storm water, sewerage network, and there is one more additional network of what this tertiary treated or treated wastewater network. So that maintenance issue will be also there. Tariff for the fresh water and recycled water, that is a big issue. As in particularly in India, we are supplying fresh water at such a subsidized rate. So say for example, in Mumbai, domestic purpose, we supply at almost ₹5 per 1,000 liters. And if you go for this particular treated water with them additional cost, nobody will ready to accept that. So this tariff, it is to be discussed, and for that purpose, proper policy has to be framed. Public awareness, very important aspect, because say even today also, people are under impression, yesterday's fresh water is they are considering today as a stale water. That is what the overall impression about the public. So we need to explain them. We need to make them understand. We are only giving the examples of Singapore, but it is necessary. And we are talking only to use it for the non-potable purpose. We are not talking about the potable purposes. No doubt we are thinking about later on it can be added. Restriction on reuse and recycled water, particularly human touch. So all this aspect, see, particularly health and safety aspects are very important when I talk about this particular term. Then assurance of the quality of recycled water. The people, the citizens, they should be 100% assured that whatever treated wastewater they are getting, it is having proper quality and having good quality, proper standards are maintained, and nothing is wrong in using that treated wastewater. So that assurance is also very much important. Then after, if we go with this new project with recycle and reuse planning, then we are expecting all these achievement. That is what conservation of environment, improvement in the public health of the Mumbai city, improvement in sea aquatic life, improvement in bathing standards of the at sea coast, air quality improvement, recycle and reuse of water that is but natural, and reduction in the demand of the fresh potable water. Say in Mumbai city also the fresh potable water demand is also increasing day by day, and we are bringing our fresh potable water far away from the 150 kilometer away from the city. So if we have to generate a new sources of fresh water, we have to go still far, 150 kilometers still far. So why not to use for this recycled water? So that is also one additional advantage. I would like to show, okay, this is what our Bandra plant, and we made one model out of that. The main aspect is what this our Bandra plant is strategically located at a strategic decision near our ceiling, and this particular plant we are planning to provide some different apart from the secondary tertiary treatment facilities will be there, but there will be some make-or facilities will be provided, and that is what it will, that plant itself, it will be a sort of a visiting, it should be a visiting place for the citizens of the Mumbai. You can say total green cover, the plant is covered with the total green cover, and public and citizen, common public, they can also visit in the plant. They cannot enter into the plant, but they can have a idea, they can enjoy the greenery above the plant. So that is what the idea, and for that purpose we have planned the make-or facilities. In make-or facilities, next slide.
So
see, this is what
2 minutes.
Yes. 60% green cover, and this is only for Bandra. There will be a knowledge center, auditorium, library, display of project, viewing gallery, interconnecting skyway, fountains and murals. See, apart from that, recycle and reuse, particularly at Bandra plant, there is it is located at a strategic decision. So common public of Mumbai, they can visit that plant as in a good way, and they can enjoy that facility. No doubt, all safety aspects are covered. So as a result, they cannot enter into the plant, but they can enjoy all these facilities as a make-or facilities of the Bandra plant. So this is how we are planning. In conclusion, I can say multiple challenges are faced while planning the wastewater treatment project with recycle and reuse facilities in mega city of Mumbai, particularly Mumbai. Recycled wastewater is a sustainable source of water and need to be used strategically, as we are still relying on the rainwater, and we are at the same time, sometimes that rain may change here and there because of the global warming and so many other issues, a different separate point for the discussion. So whatever the wastewater is available, almost 3850 mld of the fresh water is supplied every day. Out of that, whatever wastewater is generated, and we are planning for 50% of the recycle and reuse at the beginning. So that can be a good source of the water, and it will reduce the need for the potable water. Thank you. Thank you.
Dr. Selvi, thank you very much for that wonderful look at what's happening in Mumbai. We've had again large number of questions come in for you. Just got time really to choose, I think, one from the list. What would you say are the critical factors to be considered for wastewater reuse to agriculture with minimum treatment?
Say regarding Mumbai is concerned, it is a purely city at present. Inside Mumbai, the agricultural lands are not available as such. So when we are talking about the recycle and reuse or use of treated wastewater, mainly it is for a non-potable purpose, for the car washing, for the flushing, for industrial areas, and or for firefighting, for railways. This is, or even for the defense sector. So these are the main our areas of the focus. Even if possible for the construction industries, all these are the aspects we are focusing on that. And at present, this as the agricultural sector is far away from the Mumbai city, so we are not thinking about that. No doubt, see, this is a project planned for the 4 to 5 years down the line. We are definitely thinking about after further treatment with the RO and all, it can be whether it can be used for the potable purpose also with the say by mixing and all. That is also some planning is there. but not today as such. At present, it will be for the non-potable purpose.
Okay, Dr. Selvey, thank you very much indeed for your presentation. My sincere apologies again for the mistake in the introduction earlier. For everybody's benefit, Dr. Selvey is, of course, the executive engineer for the Mumbai sewage disposal project. And no doubt the plethora of questions that have come in for you will be forwarded to you by the organizers. Our next presentation is from Sylvain Donaz, who is the Deputy Director of Strategic Development with Suez, and he's joining us from France. His case study is biomass densification to improve efficiency and quality of wastewater treatment plants. And in particular, he'd be featuring the cases of Dijon and Nice. He's going to be talking about how biomass densification is applied to CAS systems and how it upgrades and increases treatment performance, quality, and process robustment of wastewater treatment infrastructure for both brownfield and greenfield applications. So now I'd like to hand over to you, Sylvain.
Thank you very much, Mark and Kailash, for your invitation. I'm very pleased to participate to this Indian Water Innovation Week from Paris today. We wanted to share with you today the exciting works and last development we did for our most recent go-to-market solutions. As you know, we are very active, like all players on water reuse today, especially also in Europe and in India. And in Europe, there is a high development of micropollutant removal, which requires a lot of tertiary treatment solutions. And what we wanted to do today for this presentation is to show you what we wanted exactly to improve the secondary treatment and showing how can we produce better water quality from the secondary treatment from existing and new plants. Why we have developed this technology, I'm going to go in deep dive to show you what is biomass densification. But first of all, we wanted to show you why we went to this new development and go-to-market solution. In France and in major part of the world, there are top 3 OPEX in wastewater treatment plants. When you exclude manpower, which is depending on the country where you have to deliver good water quality for the environment. But when you take over manpower, you find out that there is energy, sludge and reagents that are on the top 3 level of operational cost. And as a Suez, we are an operator, a technology developer, and we wanted to make sure we select the best solution for secondary treatment to make sure that we use the best energy efficient solution. Therefore, we wanted to work on future solutions based on those top 3 OPEX, which are energy, sludge, and reagents. What we have done is to look at the operational base of Suez, and we have dealt with more than 1,500 wastewater treatment plants in France, and we have benchmarked all the energy efficiency based on the water technology applied for secondary treatment. Those data represent 18 million population equivalent capacity as a whole, and each one blue dots that you see here on the graph on the top of the slide are representing one water treatment infrastructure. So based on those analyses that we did from our operational base in France, we have noticed that the most and best energy efficient water treatment technology are conventional activated sludge that we call here CAS, and of course SBR, sequential batch reactor, and also biofiltration. So based on those status and analysis, we wanted to see how we could improve those CAS system, conventional activated sludge, and SBR system. So we have worked in the past 3 to 5 years on a new concept that is biomass densification that implements a very precise controlled microbiome shift of the existing process, whether it is a brownfield existing plant or a new one that you want to build in greenfield. So we have worked on a microbiome shift that transfer the activated sludge, the former activated sludge of flocculated biomass, to a new densified biomass, which is more heavy, which is denser, and which has a more cost-effective, operational effective performance. This biomass densification is made of aggregates that have a size of greater than 200 micrometers that we increase in the biological system through a specific control microbiome shift that we implement. We have decided to, sorry, I need to get back. We have decided to implement this new microbiome shift in two types of treatment technologies, which the first one is continuous flow reactor of conventional activated sludge. So it's all about having a baseline with conventional activated sludge that you're going to shift down and up to a better, efficient biomass with a much lower and faster settling abilities, thanks to a new control system. So these are for continuous flow reactor. For sequential batch reactor, we wanted to implement exactly the same shift of microbiome to increase the performance and of the plant, and this has had to be done on a SBR sequential batch reactor system. So I'm going to present you the two solutions, the two full-scale development that we have finalized and validated in France on two separate plants, one in central France and one in south of France, where we had a continuous flow reactor applied with biomass densification and a sequential batch reactor. As you can see, conventional activated sludge are most of the time applied for brownfield projects, existing plants, but we can also apply it for new greenfield projects. And when a footprint is concerned for greenfield projects, of course, SBR are of good choice because they provide a lower footprint that can ease the integration on site. So the first concept I will present you is how we manage to implement biomass densification into an existing wastewater treatment plant in Dijon by means of a new bioaccumulation equipment that has allowed us to study and control the microbiome shift. The second concept is applied in Nice, in south of France, where we developed a new generation of our cyclor. Cyclor is a SBR solution, bioreactor, that we applied also in India recently in a Mumbai context that we've seen just before. And the challenges were part of managing the transition from conventional activity sludge to a new densified biomass and to make sure we have the best performance for this system. So the first case is based in the city of Dijon. That's the capital city of Bourgogne, where the wine is very famous in France. So you have in this color zones all the good wines of Bourgogne region that are produced there. And Dijon is the capital city, historic city, where Suez is operating and has built the wastewater treatment plant. So today, as an operator, we have validated this new biomass densification technology. So this is a wastewater treatment plant in the middle of the countryside, south of Dijon city. The capacity in dry weather is 62 MLD, megaliter per day, up to 110 megaliter per day in wet weather condition, and the plant is treating about 400,000 population equivalent. So what you can see here is that this plant is made of 4 different lines, totally independent that allowed us to implement and test in real conditions the famous microbiome shift using biomass densification. So we have integrated the new technology, which is in fact a new process approach of how to handle biomass into a bioreactor system. This has been done very quickly in less than 3 weeks time with a new equipment system with a new process control approach. So this was the site implementation that you can see here on the bottom right of the presentation, and I will share with you the nice performances that we achieved all over 1 year period, which means here in continental Europe, dealing with dry weather and extreme wet weather and cold conditions. So in blue, you can see the sludge volume index, which represents the settleability and the quality, inner quality of the biology on 2 separate lines. So the blue line is the existing conventional activity sludge that you can find anywhere across the world. And in a green line, you can see the densification biomass treatment line, where we have implemented from October last year to October this year, the densification system. And you can see that since we have implemented this new microbiome shift, our quality of sludge is extremely performing in much lower and more stable and most robustness conditions thanks to this new technology. We have achieved less than 50 milliliter per gram of sludge volume index, reaching today, as we speak, 35 in a continuous flow reactor system. So this technology allowed us, and this full-scale test allowed us to find new guidance in terms of design and operational rules for new biomass densification system. And now we are ready to implement it on any of the plants in brownfield and greenfield. I show you here the TSS, so the total suspended solid that we achieved in this condition, where you can see in green that the quality of the water, the secondary treated water, is much of better quality than the existing line, with lower than 10 in total suspended solids. So it's best for tertiary treatment. Also, you can see in the picture here, the densified line has no foam, no any more foam production, while the existing line is still having a lot of foam to deal with in operation. I'm going to go fast to show you that biomass densification in continuous flow reactor is a real microbiome shift from existing baseline that you can see here in blue to a new green and greener biomass that is more robust and allow you to reach better performance. And this is a new publication that we are releasing very soon. So there are lots of implication, improvement, impact of all the wastewater treatment plants across the world, and we are ready today to apply this concept in any of the plants to improve the quality of the water before any new tertiary system, whether it is for wastewater treated water reuse or micropollutant treatment. Last but not least, in the French Riviera in Nice, in the south of France, you can see the city of Nice on the French Riviera. Suez is operating and has built the wastewater treatment plant. This plant, you can see at the bottom, is very in a narrow footprint conditions. So therefore, we studied the new SBR cycler version using densified biomass that you can see here with the French government. We have tested it and validated it using a new type of system with new key hydraulic upgrade from our existing conventional cycler system that we have used to build a new generation of it. So we did a strong hydraulic engineering based on our existing cycler. We improve our existing cycler, improve the biomass condition through a new hydraulic. So I show you that we worked on very tough hydraulic conditions that we master in deep detail to manage the best, I would say, interaction between raw wastewater and the new densified biomass, so that we are sure that the best conditions are met. And we have applied this system across a 6-month period minimum. It's been running now for more than a year, and we have validated the performance of the new system with a very low SVI and stable and robust, thanks to the biomass densification system. I will go fast on those graphs. It's just to show you the operational data. You can see that we targeted, of course, nitrogen 10, because we are working always at this level for European regulations, which are very close today so far to the new discharge standards in India. So we are very on the same type of solutions that you need to apply in India. And of course, we have validated that the TSS were less than 15, and we have reached an average value of 8. So we have validated the good water quality, improved water quality with the new biomass densification SBR. So I would like to first to thank you, but to let you know that we are very excited to share our last development with this new concept, which is a microbiome shift, a controlled microbiome shift that we can implement in any bioreactor. And today, this is our most recent result that we're going to share more and more. And our most recent go-to-market solution, as you have seen, are based on continuous flow reactor and sequential batch reactor that we can apply either in brownfield expansion project, retrofitting, but also in greenfield, whether you have footprint constraint or not. I thank you for your attention.
Sylvain, thank you very much for that wonderful presentation. We're running a little bit behind time, so we haven't got time to go into all of the questions, but I understand that this solution has been developed as a ready for now solution for operators around the world. Is that right?
Yeah, Mark, we are ready to deliver any greenfield or brownfield infrastructure with those solutions.
Okay, fantastic. Sylvain, thank you very much indeed for that presentation. I'm going to now move on to a presentation about Singapore and the recycling and reuse of treated wastewater there. It's being given by Anil Kumar, who is the Managing Director of Royal Haskellning in India. So I'd like to hand over the floor to Anil now.
Okay.
We can.
Thank you, Mark. I think we have seen some of the wonderful presentation given by earlier panelists, and I will be presenting for about the Singapore model, what I have learned professionally, what has been done by Singapore, and I'm proud to say that in my previous association, I was associated with some of the programs done by Singapore government and how they are managing in recycle reuse of treated used water. I've used a terminology here, used water, and so just in short brief about my company, Royal Haskellning DHV is almost 140-year-old organizations. We are top independently owned engineering company. We have a workforce of around 6,500 people, and we are present in 140 countries. We work into 4 domains: water, maritime and aviation, industry and building, transportation and planning. And with respect to the water, we have some great, I would say, technologies and tools in place, and some of these are Neridas, Epherias and crystal actors. The top 5 are into wastewater treatment technologies, and bottom 5 are the artificial intelligence and machine learning tools which we used in the water supply and wastewater treatment technologies. So that's what we do. We are very innovative company, and now moving towards our my today's presentation is like we understand the problem, like what the standard and traditional practices which are in place with respect to the public treatment of wastewater. Earlier, the situation was more towards public health protections, and we had very linear solutions. We used to have abundance of water resource, and the urban population was less comparatively 50, 60 years ago in the countries like India. But now future is now we have rapid urbanizations, and we have a lot of emerging challenges happening. There is a big nexus between water, energy, food, and environment. Then we are seeing a lot of climate issues, especially into the coastal cities and dry areas. The economics of water is changing. Like we can pay for the cell phone top up, but it's very difficult to pay for a common man to pay for the tariff for the water use. That's another challenge in Asian cities. Then we have limited space, as mentioned by Dr. Salvi in the MCGM presentations. We do have a lot of physical and social livable and productive cities. That's another infrastructure needs of the day. Then we are coming across a lot of technology, sensors, and data these days, and that's where giving us a new thought process how we can move towards recycling and reuse of uh, treated wastewater, which can be used for directly for drinking or non-drinking water use. So Singapore is one of the country which has taken this initiative, I would say 20 years ago, and they have used a lot of smart technologies to become a water resilient and efficient management of their, I would say, water resources. So this is what picture of Singapore's today what we see, very neat and clean, I would say, city, and very well managed water resources, and that's what we see today. But yes, 40 years ago the situation was very very different in Singapore. These are some of the pictures of Singapore 40 years ago, and 1960s they had faced a lot of challenges on water resource management, and there used to be water rationing actually happening in the earlier 60s. And besides this, there were a lot of public health issues with respect to the things were really into poor shape, and there was not even proper sanitary and sanitation situations in the Singapore. So that's what it was actually in the 1960s. The rivers were extremely polluted, and what the government an initiative done by former Prime Minister LKY, they have made a policy where water is dominated in every other policies, and every other policy has to bend their knees for our water survival. So this was the, I would say, key message which has gone to from the top leadership level to all the departments in Singapore. And with these efforts, every policy in Singapore has water has a place. And with those efforts, the program started in recycle reuse program started in early 1970s, because of they had a relationship with Malaysia. They had a couple of agreements with Malaysia which are going to end very soon. So, and the concept of new water, which means treated wastewater, was launched in 2000, which means that collect every drop of water and reuse it as much as possible. And currently 30% of the demand, approximately 400 mgd, is met by new water, which means treated wastewater. And they are aiming to have this 60% demand by 2030 and produce new water of to the level of drinking water qualities. Currently, they are using this treated use water for industrial applications and also indirect drinking use. And they are blending the treated wastewater into their reservoirs, and then they are supplying it after treatment to the public. It's a very successful model which has been in talks from many years, and there's a huge public acceptance of this model. And the government has spent a lot of money on public acceptance education programs, including stakeholder engagements, and including some of the stamps has been created by the government on recycle reuse of wastewater. So how they have achieved this? So most of the water comes from Malaysia with two agreements and main source, and they see that as a risk for the country in the next, I would say, 20 years or so. They saw that risk in early 2000, and they took an initiative, creating one department which can manage the entire water cycles. And they have diversified the water resource into four national taps. I will talk about four national taps in the next slides. So all the water supply sources comes under one department. They had a unified agencies. They made a national theme, and they prepare a strategy so that this sustainability concept into water management can be adopted into the Singapore water management. And the four national taps which they identified is stormwater management, rains, seawater, and treatment of used water. So from these sources, they have developed their infrastructure, like treatment of used water, which is normally they say we say wastewater, they call it used water. They reclaim this treated water, and they use it to mix it with the source of their water supply. Then they are also managing their storm water management, collection of rainfall into their drains and reservoirs, and they are using that water now for their potable purpose. So that's how they are managing. I think most of their water, including their wastewater, is treated, collected very well. So the journey started in from 1998 onwards, and in 2010 they have completed almost 5 plants which are producing new water. And PUB has taken as a initiative, as an entity, to manage this entire initiatives for Singapore government. So the concept of new water, what they did is they had a traditional wastewater treatment plant, which they call it water reclamation plant, and that water is used in the new water factory. And in the new water factory, they produce uh, water which can be called new water, and it is used for various purposes now in Singapore. So the production process they have adopted in the new water factory is the treated used water is passed through microfiltration, ultrafiltration, then it goes through reverse osmosis process, and then it is disinfected by using ultraviolet disinfections. And in fact, they use this water even for drinking purpose. If you visit these plants, you are served with these bottles actually. And I myself actually drank this water a couple of times whenever I visited Singapore. So one of the great initiative they have taken is they have worked on the managing their organization setup. They made a steering committee which is chaired by the Prime Minister itself. So there were various panels they have formed, right from the consultant, technical committee, expert panels, and they started with their sampling and monitoring programs, then followed by demonstration plan, and they also had a health effect study team in place. So all these core organizations are responsible to manage the complete new water. Still this structure is going on in Singapore. Currently, through sampling and monitoring program, they are monitoring 295 water quality parameters, which is over and above the 100 parameters specified by US EPA and 114 specified by WHO. So this is the most comprehensive water quality study which Singapore government does as on date. And there are wide varieties of categories of parameters they are monitoring, and they are following the best laboratory practices. They have a very good QA/QC team and lot of analytical protocols they have set for many other countries. And the quality of data they manage is really good, and it's helps in managing a lot of troubleshooting which they are coming across in the I would say loadings they are getting into their wastewater. So as on date, they have done 140,000 tests of these samples, and still this list is actually increasing with the number of tests they do every day. So consistently, they are meeting all the latest requirement of US EPA and other agencies guidelines, and they have been actually informing these various bodies on regular basis. And if we compare these local reservoirs like raw water reservoirs or tap water supplied directly from reservoirs or US EPA standards with a new water factory, the kind of treatment they are doing is wide above the key requirements of various parameters like turbidity, total dissolved solids, or any other heavy metals or dioxins or total organic carbons. So the currently treated water is actually well above these standards, actually what they have it in place. The use which they are doing for out of this new water is they are using direct non-potable use, and they have been the target is by end of 2020 40% of Singapore water need will be met by this, and they are also using it for secondary purpose like indirect potable use in the industry also. And if we see this pie chart, the almost your new water is covering more than 50% of use in the Singapore. That's what their target is in the next 5 years or so. Currently it is mixed with the reservoirs, as I said earlier, and the entire commercial and industrial activities dependent on new water, and as they are moving forward they are entering into domestic water supply also. The other use of this water is they are using for general washing, toilet flushing into their new buildings and infrastructure what they are creating. They are using it in hospitals, cooling towers, commercial buildings, institutions. They are also using it for various petrochemical industries, power plants, and manufacturing industries. They water. Besides this, that's what new water is. But the most important part is how do we choose words like Dr. Ajit Salvi was mentioning that can we use the terminology called used water versus wastewater? It's just a mindset, public perception on the use of terminology. Then reclaimed water versus new water, or water reclamation as versus sewage treatment. So if we think about these terminologies, it changed the mindset of the public, and they have now more emphasis on concept, on some of the new concepts, some of the new RO technologies. And besides this, the media, opinion leaders, and public played important role. These all were the stakeholders who were engaged, and Singapore government has spent a lot of time and money in engaging their stakeholders. Some of the examples like what we see when this new water demonstration plant has come up, and how media and various countries were familiarized with this concept, how the features were evaluated, how various documentary films were created in various languages so that people are educated. Then various university institute experts opinions was taken so that the projects is endorsed by the water experts. Then besides this, the most important part was there was a commitment from the leadership. There was a lot of political backing to meet these challenges. There was involvement of government officials with the government. Then these leaders have worked with the public to reach out to the community levels. So that level of investments and time has been spent by the people. Then a lot of public engagement has been done. So various how to decide type of recycle format, like various issues we face in Indian cities like land availability and end use. These are the deciding factor for the technologies. In India, we do not have any. We have draft national policies, but yes, policies are framing up actually into recycle, reuse of treatment water. And currently we are dependent on many other I would say sources of informations, which in our cities, our many of our industrial area, we are following these guidelines. And in the end, just to summarize, is actually technology is only a small part of solutions to the water problem. Actually, it has been also said by Dragon Selvis earlier. And the most important part is there is I would say involvement of society and governance and natural urban system. These three areas play a big role in solving the water challenge and bringing sustainability into our systems. With that, Thank you very much. Thank you for your time.
Anil, thank you very much for that fascinating look at Singapore, which is always a great story in water use and how the lessons that have been learned there can be applied to India is particularly interesting. There are a number of questions which have come up, but unfortunately we are running over time. So we will have those questions forwarded to you afterwards if you can answer them then. Our next